it's 8 o'clock. Okay. Good morning, everybody. Okay, let's see. You have homework due this weekend, and you'll have homework due next weekend, but that'll be the last homework. Okay, so 2 more homework grades to come in.
So the homeworks are due on, instead of Friday, they're due on Saturday?
Yeah, we decided to relax it a little bit because both Mr. Miller and mostly grade our homeworks on Sunday. So normally I couldn't collect them on Saturday. Okay, let's see. Let me go to shared screen. Mr. Bennett came to my office hour yesterday and asked me about, was it problem 7 on your homework?
Hold on. I have one question. What days are final exam?
Oh, gosh. It says in the syllabus. I don't remember right offhand.
Okay, so look in the syllabus to see when yours is.
Yeah.
All right. I'll do that.
Okay. Yes, problem 5. Okay. And it says, oh, all right. Let's go to my screen here. There's Mr. Miller. Okay, it says find the domain of F and then find F inverse and its domain. So here's a similar problem. You can only find the inverse of one-to-one functions, of course. Other functions, if it's not one-to-one, it doesn't have an inverse. And to get the inverse trig functions, what we had to do was to cut the functions down to a one-to-one piece and then find the inverse of that. And that has problems that come with that too. But okay, let's not worry about that right now. Let's find the inverse of this function. F of x is 1 plus e to the x over 1 minus e to the x. And to do that, what you do is, okay, let's set y equal to 1 plus e to the x. And you solve for x in terms of y. So instead of having a function of x, you'll have a function of y. Okay. And then you interchange the x and the y. So let's do that. Okay, so I start by letting f of x equal to y. And I now want to solve for x. Okay, so how am I going to do that? Well, what you do depends on what function you are given. Let's see, I'm going to multiply both sides by 1 minus e to the x. Excuse me. So that'll give me y times 1 minus e to the x is 1 plus e to the x times 1 minus e to the x. No, excuse me. Sorry, that's not right. The 1 minus e to the x cancels. Well, all right. So just write that. There. Okay. So now we have y times 1 minus e to the x is 1 plus e to the x. And now I'm going to expand this side. So y minus y e to the x is equal to 1 plus e to the x. And then, let's see, I'm going to get the terms that have x in them on one side and the other terms on the other side. So if I subtract 1 from both sides and add y e to the x to both sides, that'll get it. Oops. Okay. Y e to the x plus e to the x. Okay. And what that does for me, now I can factor out an e to the x. On the right-hand side. And then I can divide both sides by y plus 1. Okay. And then to get x by itself, take the log of both sides. And ln of e to the x is x because ln and e are inverses of each other. A function undoes its inverse. In fact, I'll show you how that works with this particular function later here. Okay, so we got x is equal to log of y minus 1 over y plus 1. So I've got x written as a function of y. And now let's just interchange the x and the y. Okay. Or you could leave it this way, okay? That's just changing the name, basically. So y is ln of x minus 1 over x plus 1. And that is f inverse of x. This was f inverse of 1. So that's the inverse function. Any questions? Okay, so that's what you're going to do with those problems in number 5. Well, now let's find the domain. Of both functions. The domain of f, okay, so f of x is 1 plus e to the x over 1 minus e to the x, yes. Okay, so what's my domain going to be? Well, e to the x is defined for all x, so no problems there. The denominator cannot be 0, okay? So the question is, when does that happen? Well, it does happen if x is equal to 0. 1 minus e to the 0 is 1 minus 1 is 0. Okay. So the domain of f, all reals except 0. Okay, that's the domain of f. How about the domain of its inverse? And okay, let's write down what that is. Y, that is ln of x minus 1 check to make sure I've got it written down correctly. Okay. Well, I've got to worry about a couple of things here. First of all, that denominator cannot be equal to 0. So x cannot be minus 1. But I have to worry about something else too. In order for the natural log to be defined, x minus 1 over x plus 1 has to be greater than 0. Okay, because that's inside the natural log. So we need x minus 1 over x plus 1 to be greater than 0 so that it's in the domain of the natural log function. All right, so that's an inequality. A lot of times when I'm trying to solve inequalities, okay, yeah, I want to find where x minus 1 over x plus 1 is equal to 0. Okay, first, if I can find that, then I have all the places where the function can change from positive to negative, and all I've got to do is check my intervals. Well, it's equal to 0 when x is equal to 1. And we already threw out the x equal to minus 1. Okay. All right. So x equal to 1's not allowed. Because then I'd have ln of 0. But I still don't know the answer to this. So I'm going to do the following. A number line. Okay. Where is the function not defined at minus 1 and plus 1? Okay, here it's equal to 0. Well, not the function, what's inside the log. And this one we get because x plus 1 would be equal to 0, and it's in the denominator, and that would automatically not be allowed. Okay, but those are the only two places where x plus 1 can change sign. So let's check a number in each interval. How about minus 2 over here? We would get minus 2 minus 1 over minus 2 plus 1 is minus 3 over minus 1 is a positive number. Okay, so this is in the domain. Zeros in between here. I could use that to check the interval from minus 1 to plus 1. Okay, if I put that in x minus 1 over x plus 1, that's minus 1, that's negative. Okay, so this gets thrown out. That's where you get a negative number inside the log, and that's not part of the domain. What happens over here? I could check 2. We get 2 minus 1 over 2 plus 1. That's positive. I shouldn't write equals positive there. It is positive. Okay. Okay, so that interval's in the domain. Okay, so the domain so first of all, x minus 1 over x plus 1 is greater than 0 when x is in minus infinity to 1 and x is in 1 to infinity. And that's exactly when. Okay. So the domain of f inverse is minus infinity to 1 union 1 to infinity. That is any number in either one of those intervals. So we found that domain. Okay, any questions now? Somebody wants in? Okay. Are you all still there?
Yes, ma'am.
Okay, thank you. Now, this is the kind of thing you're going to do for problem 5. Okay, that's kind of interesting, I think. Oh, let me show you first of all that this is true. No, cancel. Okay. If f inverse really is the inverse of f, okay, if I find a function g and I'm claiming that g is a function of is the inverse of f, okay, if g is the inverse function of the function f, so f and g are functions, then the following is true. For x in the domain of g, f of g of x is x. And for x in the domain of f, g of f of x is x. That's what it means for one function to be the inverse of the other. Let's check that. Okay. So we have f of x equal to look at my notes. So I'll have to scroll back up. F of x is 1 plus e to the x. And we have f inverse of x. We computed that to be ln of x minus 1 over x plus 1. So let's do f of f inverse of x. And I put in f inverse of x, that's the log of x minus 1 over x plus 1. And that's equal to 1 plus e to this whole big power here. Okay, so it's a lot to put in an exponent. E to the ln of x minus 1 over x plus 1 over 1 minus e to the ln of x minus 1 over x plus 1. Okay, but e and ln are inverses of each other. We've talked about that. So e to the ln of x minus 1 over x plus 1 is x minus 1 over x plus 1. Yeah, if you want to do an undo an ln, you apply the exponential function. If you want to do undo an exponential function, you apply the natural log function. Okay, so we're down to that. All this is supposed to be equal to x. Okay, so let's keep going. I'm going to get a common denominator in both the numerator and the denominator here. Okay, because they're sums, all right. And the both common denominators are x plus 1. Okay, so that's going to give me x plus 1 plus x minus 1 all over x plus 1. That's rewriting the numerator and rewriting the big denominator. That's going to be x plus 1 minus x minus 1 all over x plus 1. Okay. Well, since the denominator in the numerator is equal to the denominator in the denominator, okay, they're going to cancel. And then you're left with and let me distribute that minus there. Okay. All right. So I've got 1 and minus 1 in the numerator, and then x plus x. That's just 2x. And I've got x and minus x in the denominator, but then 1 plus 1, that's 2. That's equal to x. So check on that. Okay. Let's do the other way. Let's compute f inverse of f of x. That's supposed to be equal to x2. Okay, f of x, that's 1 plus e to the x over 1 minus e to the x. And that's equal to, okay, this time x gets replaced by, yeah, wait a minute. No, but this goes in the ln. Okay. Okay, so f inverse takes ln. All right, this is what I put in the place of x in the definition of that f inverse function. So I get all of this 1 plus e to the x over 1 minus e to the x minus 1, and then 1 plus e to the x over 1 minus e to the x plus 1. Okay. And that's supposed to be equal to x. But let's see, I have a bit of doing to get there to show that's true. Okay, so I'm going to work on what's inside the log first. Get a common denominator in both the numerator and denominator, and it's, again, the same thing. Okay. And then, oops, I didn't put an X there. Okay. Doesn't belong there. Okay. So then that's going to be 1 plus e to the x plus 1 minus e to the x all over 1 minus e to the x. Right. And now 1 minus e, the denominator and the numerator and the denominator and the denominator are the same, so they're going to cancel out. And I'm left with minus 1 plus e to the x all over 1 plus e to the x plus 1 minus e to the x. Okay, well, in the top, I've got 1 minus 1, which is 0, and e to the x plus e to the x, which is 2 e to the x. In the denominator, I've got e to the x and minus e to the x. That adds out, but 1 plus 1 is 2. So that's equal to ln of e to the x. And because the natural log and the exponential function are inverses, that's x. So that works too. Okay. So you can always check if one function is the inverse of another. Any questions? Well, I was thinking about this function. It's kind of interesting. Okay, so it's got domain x not equal to 1, 0, x not equal to 0, okay. And in fact, you're going to have a vertical asymptote there. And then I thought about, well, what the domain of the inverse function is two disjoint intervals. You have to leave out everything between -1 and +1. That's a little odd. But let's see. Because f is 1 to 1, it must be either an increasing function over its entire domain or a decreasing function over its entire domain. And okay, well, I was playing around and took the derivative. It's increasing. So, well, let's just check that. Yeah, I was just thinking this is kind of interesting. I'm not going to completely go through all the details of the graphing of this function, but okay. So f prime is equal to, okay, derivative of the top, be e to the x, times the bottom, minus the top, times the derivative of the bottom. Okay, well, the derivative of the bottom is going to be minus e to the x. And then that's over the bottom squared. And let's see what happens there. Well, I can factor in e to the x out of the numerator. Let me combine this minus and that minus. That becomes minus minus is plus. Okay. And then I can factor out that e to the x. And let's see, e to the x and minus e to the x add out. So you wind up with 2 e to the x, 1 minus e to the x squared. Well, that's positive. Always. Okay, because e to the x is always positive. And in the denominator, you have something that got squared. That's positive as long as it's not 0. Okay, and it is 0 at 0. But whenever it's defined, it's positive. So f prime is greater than 0 for x in the domain of f. Means f is increasing. Increasing on its entire domain, which would be minus infinity to 0 and 0 to infinity. Okay. Well, what are the asymptotes? The horizontal, okay, so for the horizontal, check two things. The limit as x goes to infinity of f. Okay, so that's the limit as x goes to infinity of 1 plus e to the x over 1 minus e to the x. And this is the infinity over infinity form. Okay. Which is indeterminate. But we can figure out this one without pulling out a calculator and kind of doing something crude. I can rewrite this. I'm going to multiply the top by 1 over e to the x and the bottom by 1 over e to the x. So I'm multiplying by 1, which doesn't change anything. And that gives me 1 over e to the x plus 1 over 1 over the e to the x minus 1. Well, I know that the limit as x goes to infinity of 1 over e to the x is 0. E to the x, as x goes to infinity, e to the x goes to infinity, and we talked about it, it goes to infinity fast, okay? So you're looking at 1 over large numbers. Those are small positive numbers. The limit's 0. So that means this limit is 1 over minus 1 is minus 1. And so, yeah, y equal to minus 1, and that's in the positive direction. That's a horizontal asymptote. What about the negative direction? Okay. Okay, in the negative direction, okay, the limit as x goes to minus infinity of e to the x is 0, right? Because e to the x looks like that. So if x is going to minus infinity, that limit's 0. So this is just 1 over 1, which is 1. Okay, so y equal to 1 is a horizontal asymptote too. And that's in the negative direction. What about vertical asymptote? The only possible place would be 0. So I need to check. The limit as x goes to 0 from the right. And okay, well, if this turns out to be infinity or minus infinity, it's a vertical asymptote. That is x equal to 0 is. But there's also coming in from the left here that you could do. And I think one's going to give positive infinity and the other negative. As x goes to 0 from the right, okay, well, if I look at that function written in that form, of 1 over e to the x plus 1, 1 over e to the x minus 1. Now, no, I don't need to do that. Excuse me. Don't need it. This is x going to 0, not x going to infinity. Okay. So scratch that. I don't need that at all. As x goes to 0 from the right, e to the x goes to e to the 0. So this is just going to be, I'm just going to plug in. It would be, no, I can't just plug in. Okay, get your wires uncrossed. Let's see. Yeah, because I'm going to get 1 minus 1 in the bottom. All right. Okay, so yeah, that's fine. This is going to be minus infinity because this is of the form. As x goes to 0 from the right, we're going to have 2 over minus infinity. Okay, that's a form and not a number, but it's not an indeterminate form. Not 0 over a large negative number, so not a positive number over a large negative number is a number. No. Okay, that's not minus infinity. That's 0. Okay. Yeah, it's 2 over 0 form. But that's not indeterminate. It's these numbers are going to be close to, let's see, they're close to 1, but as x goes to 0 from the right, they're going to be bigger than 1. Yes. So these are small negative numbers, and this limit is minus infinity. And likewise, limit as x goes to 0 from the left of this function is going to be positive infinity, because this is, again, the 2 over 0 form. But what you get in the denominator this time, okay, is small negative numbers. No, small positive numbers, excuse me. Small positive numbers, because you're coming to 0 from the left, so your e to the x's are going to be less than 1. Yes. So your limit's going to be positive infinity. Okay, so that's a lot of talking. So that x equal to 0 is vertical asymptote, y equal to 1 is a horizontal asymptote, y equal to minus 1 is a horizontal asymptote. And okay, I didn't investigate this further. We do know that the function's increasing, so it must look something like this. Goes up, and then it comes back in like that. Okay. It's kind of amazing. It just skips over, the range just skips over that big interval altogether. So that's a little different. Any questions? Oh, goodness, I spent a lot of time on that. Well, anyway, that should get you ready to do problem 5. Yeah, this turned out to be kind of an interesting little problem, I thought. So I just kept investigating. Okay, so let's see. I thought I'd work a couple of more integrals for you. And let's see, I picked out a couple here. How about, so practice integration. Yeah, that's what problem number 7 is about. First of all, what's the antiderivative of 7 to the x? Anybody want to try? And I'll give you a hint. The derivative of 7 to the x is 7 to the x ln of 7. Are y'all still there?
Yes, ma'am.
Okay,
Is
so
it-
no. Oh,
Is
okay,
it,
somebody, go ahead.
is it,
Go,
ma'am?
go ahead.
Is it 7 to the x over ln of 7 plus c?
Yeah, very good. Who's that?
Jake?
That Okay, Jake. Okay, good, Jake. Good. Okay. Yes. All right. Yeah. If this is true, then this is true. And ln of 7, of course, is not a variable. It's just a constant. How about this one? Any ideas? What we should do? Well, okay. I don't see that I could change the form of the function.
Is it 2e to the square root of x plus c?
Okay, but I think maybe that's right. But how did you get that?
I did this practice problem from, I think it was on Dawkins or somebody's notes, and I did this practice problem.
Okay, but how did you get that? I mean, what'd you do?
Okay,
Okay.
I substituted a different variable for e to the square root of x.
I think that makes perfect sense. Okay, so what'd you substitute? So u is what?
U is e to the square root of x.
Okay, well, you can do that actually. Okay. Okay, so that means du would be e to the square root of x times the square root times the derivative of the square root of x.
Yes, ma'am.
Okay. Don't forget the chain rule. All right, so that says that 2 du, and I'll put it back in the other form, is e to the square root of x times, well, x to the minus 1/2 is 1 over the square root of x dx. Okay, but that's what's in your integral. So that's equal to 2 du. And so your antiderivative is u.
And then you plug back in for u.
Yeah, okay, that's correct. Good. Oh, yeah, Dawkins. Yeah, if y'all don't know, Paul's notes, it's done by a guy in our department, Paul Dawkins. But people all over the world know his notes. He puts them up on the internet free. Okay. I have a friend in Poland who says he uses Paul Dawkins' notes to teach his calculus classes. He asked me if I knew the guy. Yes. I do indeed. He's the most famous member of our department. Okay. Another way you could do this, well, it's just a different substitution. You could also let u equal to the square root of x, and then du would be, and that would give you 2 du is 1 over 2 times this. Oh, got rid of the 2. Okay. There. And that would turn the problem into so it was originally e to the square root of x over the square root of x. And that turns it into, I'll bring that 2 out, 2 e to the u du, but you get the same result, okay? Because u was the square root of x. Okay. Okay. Yeah, we have this one technique, which is not always going to be applicable. You're going to learn lots more techniques next semester. How am I doing here? Okay. How about this one? Okay. Oh, who told me about that one? Who was that?
That was Jake again.
Oh, okay. That was good. Good, Jake. You've been working. Okay. Okay. Well, what about this one then? Do you see a function whose derivative is in there? The function's in there and its derivative is in there.
As you said, the natural log of x and the hoop over x are derivatives of each other. So if I'm not wrong, it would be sine of natural log of x.
I think that's right. Y'all are skipping over the reasons. Okay. I think that's correct, Mr. Levy. And I know your voice by now. So you would be ln of x here. Okay. And du would be 1 over x dx. And that changes the problem too. Cosine of u du. For now, I want to see you put in these details. I care more about how you got your answer than whether your answer is correct or not. I want to see your reasoning, okay? So please provide that for me. That's particularly important in this class where I don't have you all sitting in a room taking the exams. I don't know where your answers are coming from. I want to see that you understand how you got your answer. You got to show me how you got it. If you just put in, and okay, I've been counting off already, so you know I will. You just give me the answer and you don't provide the reasons, I may well count the whole problem wrong. Okay. But thank you guys. That was good. Let's see. I still have 7 minutes. How about one more? If I can find me one. Oh, well, how about this? This is another indefinite integral. Okay. No, it's supposed to be. Okay, I don't know if this matters or not, but sometimes you change problems, you make them a lot harder. Oops. How about sticking with one variable? Okay. This is another U substitution. That is, it works here. In fact, I don't know how else you do it. What should U be equal to? Okay, we're running out of time, so how about 1 plus the tangent of t? Because then du, well, it's the derivative of the tangent, basically. That's secant squared. So it looks like it'll work nicely. And that changes the problem to u cubed du. Okay, integrating that. And that's equal to u to the fourth over 4 plus c. And that's equal to 1 plus the tangent of t to the fourth over 4. If I had not had that secant squared sitting there, this would have been a much harder problem. Okay, if I try to integrate this, I don't really know. Let's see. Well, I could expand using the binomial theorem. No, it's 3, 3, 3. Okay. Cubed of t dt. Ugh. Well, we know how to integrate that. We know how to integrate that. Oh, I know how to integrate that too. I would change it to secant squared minus 1. And then I know the antiderivative of the secant, so that'd be no problem. Tangent cubed. Well, I could write it as sine cubed. And then change 1 sine squared to 1 minus the cosine squared. Cosine cubed. And I think that would work. Okay, you're going to learn. You're going to learn about after next semester. After the first third of next semester, you'll know how to do this one. But it's a tougher problem, actually, than this one is. This one's set up for a u substitution. This one's not. Okay, well, I'm out of time pretty much. So we'll end class there. Tomorrow, I'm going to start talking about our last couple of topics. We'll talk about how you use integrals to find areas of regions. So a little application of integration. And then we're going to very lightly cover how you find some volumes of solids of revolution using integration. But okay, class is over. Hang around if you'd like to ask a question.
Have a good day.
You too.